y voy a poner la música de fondo y voy a iniciar la del seminario para que sepan.
La cámara, ya está prendida. La dejo prendida.
Sí, la puedes dejar prendida, no hay problema.
El volumen,
voy a poner la música de fondo y voy a iniciar la del seminario para que sepan.
La cámara.
Hi, Carolina.
Hi, Kristen, welcome. We're gonna give people like a couple minutes for them to join.
Sounds good. I just wanted to make sure you could hear me.
We hear you loud and clear.
And how long should I speak for?
It'll be 15 minutes for your talk. I mean, up to
how
50
many?
minutes.
I couldn't hear.
Up to 50 minutes. 50.
50, good.
Yes, and then questions. So I think we can get started. Are you ready?
Yes, should I try to share my screen or wait till you finish your introduction?
Yeah, I'll introduce you first. Bueno, buenos días, todos y todas. Muchas gracias por atender a esta charla del simposio. Hoy tenemos a Christine Lauder. Voy a presentarla primero en inglés y luego voy a hacer la presentación en español. Christine's going to talk today about private AI, machine learning on encrypted data. Christine is the West Coast Director of Research Science for Meta, IA Research, or FAIR, leading the Seattle and Menlo Park labs with groups in core machine learning, computer vision, robotics, natural language processing, and other areas. And her research focuses on private AI, homomorphic encryption, and post-quantum cryptography. She spent 22 years at Microsoft Research as a principal researcher and partner researcher, manager of cryptography and privacy research. She is elected fellow of the American Mathematical Society, the Society of Industrial and Applied Mathematics, the Association for Women in Mathematics, and the Association for the Advancement of Science. She got her PhD in mathematics from the University of Washington in 1996, and she was president of the Association for Women in Math and Mathematics from 2015 to 2017. And also she is an affiliate professor of mathematics at the University of Washington. Así que Christine nos va a hablar hoy sobre private AI in machine learning on encrypted data. Christine es West Coast Director de Research Science para Meta, IA Research, lidera laboratorios de Seattle y Menlo Park, con grupos en Core Machine Learning, Computer Vision, Robotics, Natural Language Processing y otras áreas. Su investigación se centra en inteligencia artificial privada, homomorphic encryption y criptografía postcuántica. Ella estuvo 22 años en Microsoft Research, como principal research partner, research manager of cryptography and private research. y fue elegida Fellow de la American Mathematical Society, de la Society for Industrial and Applied Mathematics, la Association for Women in Math y la American Association for the Advancement of Science. Tuvo su PhD en matemática de la Universidad de Chicago y fue presidenta de la Asociación para Mujeres en Matemática y es affiliate professor de matemática en la Universidad de Washington. Bueno, muchas gracias. And Kristen, whenever you're ready.
Ok, gracias, Catalina. Muchas gracias. Mucho gusto estar aquí con ustedes. Mucho gusto conocerlas. Es muy lástima que no puedo estar allá en Costa Rica con ustedes. Un día espero visitar. Y lo siento por la introducción muy larga, porque tú tenías que hacer las dos veces en inglés y español. Lástima que no puedo dar mi charla en español porque no conozco todas las palabras en español, pero si tienen preguntas, posible que puedo contestar en español. Entonces, voy a empezar a share screen. Dime si este funciona. Okay, from the beginning. Okay, good. Can you see my screen?
Yes, we can.
Great, thank you so much. So I'm so happy to be here. I will not see the chat if you put questions there, but if someone wants to moderate, if there's questions, you can feel free to interrupt me while I'm talking. I'll try to spend a little less time than 50 minutes in case you want to ask more questions. I recently went to Facebook AI research this past year. It's now Meta. I was at Microsoft Research for 22 years, so this was a very big switch for me. So I'm happy to take questions and about that. And in terms of my career, I also, as Catalina said, have worked very hard on organizing initiatives for women in mathematics and computer science. So I'd also be happy to take questions about that topic at the end. So the topic of my talk here is private AI, machine learning on encrypted data, more specifically. So this is really a field that I feel very proud that I've helped to create over the last 10 years. So privacy is something that is basically a societal good that I got interested in about 15 years ago as I was leading the cryptography research team at Microsoft. And artificial intelligence is a very big new trend, and I think a very, very important application of mathematics. And the foundations for artificial intelligence and machine learning go back a number of decades, but it's really in the last decade that we've seen such incredible progress of applying machine learning mathematical models to create services, which we now call artificial intelligence. So Catalina, everything okay? Can everyone hear me pretty clearly? Okay, good.
Yes, we can.
Excellent, thank you. So what I'd like to talk about today is a kind of a combination of these issues, privacy and artificial intelligence. So if you went back 100 years, what people meant by artificial intelligence would probably be very, very different. The idea of like robots or some kind of artificial life that walks around and interacts with us. Now, today, we all have our smartphones or various computing platforms that we interact with. And those platforms can now simulate human intelligence in the sense of being able to give us recommendations or input. So the most common things that we see these days in the modern world are things like getting directions from your smartphone, getting recommendations, restaurant recommendations, movie recommendations, These artificial intelligence is being used for healthcare, for predicting your various diseases that you might have, even in the financial sector. So there's a lot of services that are now available through computing platforms such as smartphones. And the real issue, the privacy problem here, is that in order to get these services, we are sharing a lot of our private data. So that's the kind of the main privacy problem. So in what sense, how are we sharing this private data? Well, artificial intelligence works as follows. Today, you collect a lot of data. So any company that wants to create a machine learning model, or for example, a research group in medicine that gets funded by some government agency and collects a lot of data about a particular problem, be it, so I've shown for many years a demonstration of heart attack risk prediction. So there was a study that took place in the United States in Massachusetts for many decades called the Framingham Heart Study, where they collected data about patients and their risk of having a heart attack and all kinds of personal information like your weight and your blood pressure and your age and all of these things. And then they use that data to create mathematical models of your likelihood of having a heart attack given all of these characteristics. So this is representative of what I mean by machine learning models. A bunch of data is collected, and then there's some mathematical model which is trained. That process is called the training process. And then this mathematical model can now be used on a new patient that comes in that gives their personal information, such as weight, height, age, blood pressure, things like that, to predict their likelihood of having a heart attack. So that's just one example of what we mean by artificial intelligence or machine learning models. And so what you can see is there's a privacy problem in two places there. There's a lot of data being collected about people in order to train these models. And one thing we can do is to have a curator of that data who's trusted, who agrees to never share that data or never go and use it for something else. And the second problem is that when you go and you want to get a prediction, so say you go onto an online service and you type in some private data, so some medical data or some financial data or something like that, then that data is now being shared with the service in order for you to get your prediction back. So that's the underlying kind of privacy problem in AI today that I'd like to talk about. And there's a lot of different pieces to that problem, as you can see. There's the training piece when the data is collected and trained, and then there's the prediction piece when you give your private data to just get a prediction. And so both parts of that can actually be solved with a new technology coming from mathematics, which I've been working on from more than 10 years now, really, since 2011. And that's called homomorphic encryption. So what I'd like to do is talk a little bit about homomorphic encryption and how it works and how we can use it to help solve this problem. But keep in mind that I'm only talking about kind of one flavor of the problem here. And there's a lot of different issues to think about in terms of privacy in cloud computing and in AI. And there's a lot of other issues in AI having to do with what we call responsible AI. And so I'm just talking about one particular flavor of the problem, but it's interesting to ask questions and think about a wider range of problems. And there's a wide range of cryptographic tools that can be used to help solve different parts of the problem. And there's a whole field of researchers working on responsible AI. And that's a broader field. And it's interesting to think about how privacy questions intersect with the goal of using AI responsibly in our world. So let me focus on the mathematics for a little while. I'm assuming that my audience is mostly mathematicians, so I hope I'm hoping I'm right in that assumption. But it's fun to think about how mathematics can be used in applications, even very pure mathematics that we study. So I'd like to start with two different explanations of homomorphic encryption. One is just a kind of a funny one. Here we have Homer Simpson, who's a jeweler, and he is being tasked with making some jewelry from some gold that I'm going to give him. But my gold is very valuable, and maybe I don't trust him. He doesn't look very trustworthy. And so instead of just giving him the gold, I'm going to put my gold in a locked box. So you can see over here on the right-hand side, this is a box, and Homer has to put his hands into these gloves in order to work on the gold. So he doesn't get trusted to just give him the gold. He has to put his hands in the gloves and work on the gold inside this locked box. Now, I locked the box. I put my gold in the box, and then I locked it with the key. And the very important thing is I keep the key. So when he's done, he gives me back the box, and I unlock the box, and I can get the jewelry out or whatever it is that is left over. And so this is an analogy for homomorphic encryption, because the gold here is private data. So the idea is that instead of giving this data to the cloud service or some other team to create a model in the clear, we're going to lock it in the box, which is encryption. So encryption plays the role of locking the box, and the data is only uploaded to the cloud in encrypted form. And then whoever is going to work on this, create some machine learning model or create some prediction, is only going to have access to the encrypted data, and they're going to return some encrypted result. And then when the data owner receives back the encrypted result, they have the key so they can decrypt it locally. So that's a description of homomorphic encryption in terms of its functionality. What does it do? What does it allow you to do? So here's a more mathematical description of homomorphic encryption. So mathematicians seem to love commutative diagrams, so I've written it as a commutative diagram. And this is also a very easy way to describe homomorphic encryption, like at a party. If someone asks you, what is homomorphic encryption? You can say, well, it's encryption where you can exchange the order of computing and encrypting. So you can either compute on your data and then encrypt, or you can encrypt and then you can compute. And when you decrypt those two results, you should get the same thing. So that's what homomorphic encryption is in terms of the property that it has. Now you can kind of see how these two descriptions are the same, because if you have some data, this A and B are elements which are your private data, and you can think of this as your gold. The idea is that you can encrypt on it first. You can encrypt it first, and then you can upload it to the cloud service, which is like outsourcing the work, giving it to Homer Simpson in encrypted form. And then you compute on it, and then you can, after the work is done, then you can return it to the data owner who can decrypt it. And that should be the same as if you kept the data locally and did the computation yourself. So that's why these two descriptions are the same thing. So usually I like to have fun with my audience when I used to have live talks and have everybody vote which description they like better. But I don't have voting buttons here. I don't have a way to do that on Zoom. So you'll have to consider yourself which description you like better. But hopefully, if you learn one thing from this talk, it will be, what is homomorphic encryption? Homomorphic encryption is encryption that you can compute on, and it won't matter that you exchange the order of compute and encrypt. So the first solution for a single operation on encrypted data, it actually goes back to the 1970s with RSA. So if I don't know how many of you have studied RSA-based cryptography, for example, in a number theory class, and RSA is used throughout the world to protect, financial communications and all kinds of e-commerce applications, along with another area of cryptography that I worked on for many years when I first went to Microsoft Research, and that is elliptic curve cryptography. And elliptic curve cryptography was introduced in the 1980s. So RSA in the 1970s, elliptic curve cryptography in the 1980s, and RSA and elliptic curve cryptography allow you to really do one operation on encrypted data. And so basically think of mathematics where you could only add things together. Like imagine a world where all your mathematics was just adding things together. Well, you could do that on encrypted data, using RSA. But that's not very useful. Machine learning models and most other computation that we do are a wide variety of functions, which are usually approximated, but through basically polynomial operations where you have to both add and multiply. So when these are even, complicated, machine learning algorithms and other type of compute, when you put it on a computer, it's usually approximated through some kind of, you have to use like floating point or fixed point numbers, like approximations to the inputs. And then you have to model on the computer, how are you going to give an approximate answer to the mathematical computation you wanted to do. And the way that's done is through circuits. So there's and or gates that make up any, computer program that you want to apply. And so the important thing in order to be able to compute on an encrypted data is that you need two operations, not just one operation like addition. So in 2009 was the first solution proposed by Craig Gentry for homomorphic encryption, which could handle two operations. But the solution was very impractical and also not based on well-known hard math problems. And so I was very fortunate in my group at Microsoft Research, the cryptography group that I led in 2011, we had several surprise breakthroughs. So Vinod Vaikunathan and Zvika Brakersky, and Vinod was a researcher in my group, came up with the first solution for homomorphic encryption based on what's called the ring learning with errors problem, which is related in a very concrete way to hard lattice problems. So this is part of now lattice-based cryptography. And I remember him coming to me in the hallway, so excited about this discovery, and we immediately started working together on it to create an actual implementation of the system that he was proposing. And that used mathematics and rings from algebra, and the ring learning with errors problem is still today the foundation for all the homomorphic encryption systems being built and deployed around the world. So what I'm going to try to explain a little bit is about the lattice-based cryptography and the ring learning with errors problem coming from mathematics that form the basis for this important technology, homomorphic encryption. So over the next 10 years, I really worked primarily in this field, and first trying to make the operations, the compute and encrypt and decrypt, all very, very practical, but also trying to understand the hardness of the underlying problems, which I still work on today, but also working on the applications to machine learning. So that's when I really started working with machine learning researchers, and we kind of created this whole new field, which we call private AI. So it means being able to do machine learning and artificial intelligence on encrypted data. So our really big breakthrough, we had a big breakthrough in 2012, which was showing that we could train machine learning models on encrypted data. And that paper was called ML Confidential, which was supposed to be a takeoff on the movie LA Confidential. And then our 2016 paper was showing that we could do actually neural net predictions on encrypted data. And that was called CryptoNets. So that was very surprising at the time that we could even approximate evaluation of deep neural nets to do valuable predictions on encrypted data. So now that I've kind of told you what is private AI and how does homomorphic encryption enable a solution for privacy in machine learning and artificial intelligence, I'd like to talk a little bit about the mathematics of homomorphic encryption and the lattice-based cryptography. I wonder if there are any questions. Should I pause for any questions right now?
We don't have any questions on the chat right now.
Okay.
If people have questions, and if you don't mind, I can interrupt and read them to you.
Yes, please do. Please interrupt if there's any questions. So I mentioned RSA. You can see the comparison of lattice-based cryptography was really introduced in the mid-90s by Hofstein, Pfeiffer, and Silverman in 1996, and they created the company NTRU, actually, coming out of their proposal. Independently in the computer science community, it was introduced by Itai and Dwork. So you can see it's a little bit newer than RSA and elliptic curve cryptography, which I mentioned earlier from the mid-70s and the mid-80s. But still, the hard math problems in lattice-based cryptography have been around even longer than that. So the hard lattice problems are like the approximate shortest vector problem, and I'm going to show you a little diagram and explain that in just a minute. But there were already, there's more than a 30-year history of mathematicians working on hard lattice problems, such as the shortest vector problem. So the lattice basis reduction algorithms, which are used to attack hard lattice problems, started really with LLL in the mid-80s, so more than 30 years ago. So in cryptography, it's always really nice to have problems which are the basis for your security of your systems, which have been around for a long time, because then we have some confidence that mathematicians have worked on these problems and have really tried to understand how hard they are. So RSA, for example, is based on the hardness of factoring, and factoring integers is a problem that's been around for centuries. And so that's very nice because, when RSA was created, they thought that, it would be secure for many, many decades at the parameter levels that they chose. But in fact, mathematicians came up with new algorithms in the 80s, which provided sub-exponential attacks on RSA and really changed the parameter settings. And those algorithms were like the number field sieve. So if you're in number theory and studying things like the number field sieve or the quadratic sieve, more simply, then you can see some new interesting ideas that were brought to bear and led to an unexpected breakthrough in the attacking the hard problem that was used for cryptography. So just to be clear, that same thing can happen today for lattice-based cryptography. We think we know how hard this problem is, but mathematicians could come with new ideas and attack the problem in new ways, and then our understanding of the hardness would have to be adjusted. But today, what we can say is based on the history of lattice basis reduction algorithms and how much time they take, how much resources they take in terms of storage, we can say that the parameters we choose are such that the best known classical attacks run in exponential time. So exponential time means that it takes time which is exponential in the dimension. So if the dimension is n, then the attacks run in time like 2 to the n. And in addition, a nice feature is that we do not know any polynomial time quantum attacks. So even when a full-scale quantum computer is built, we do not yet know any way to use that to attack these lattice systems in polynomial time, in quantum polynomial time. And that, for example, is not true for RSA or elliptic curve cryptography. We now know polynomial time quantum algorithms for attacking both factoring and elliptic curve crypto. So when there's a full-scale quantum computer, a lot of the cryptography that's used today around the world to secure e-commerce will no longer be secure. And so that's why there is an ongoing 5-year competition being hosted by the National Institutes of Standards and Technology in the US, but it's an international competition to select new candidates for post-quantum cryptography to replace RSA and ECC. And lattice-based cryptography is one of those candidates. So what are the hard problems? So you can think of a lattice as just being basically a discrete linear subspace of Euclidean space. So here I'm showing it in 2 dimensions, but just think of n dimensions, and then just think of some basis like of n-dimensional vector space and all of the linear combinations of those basis vectors, and that is a lattice. Now here in 2 dimensions, I'm just showing because that's the only thing that I could draw on my PowerPoint slide. I'm showing you a very nice basis. So think of this, or the origin of these vectors as being the origin of the plane. So think of this as being 0, 0. And here you have 2 nice short vectors, and these 2 vectors generate every other element here. And as you can see, it's pretty easy to think about how to decompose. So if you're given a random element, oops, sorry, clicked on the wrong thing. If you're given a random element of this lattice here, you can kind of see how to write this as a combination of basis vectors, because the lengths are short, and you can just kind of go over here until you get to about this distance, and then you can go up here until you get to this distance. So this is in the real plane, the real numbers plane. And I'll say in a minute how we're going to convert this into finite fields for cryptography. But so in the real Euclidean space, so now think of this same lattice, but with a different set of basis vectors. So you can see how these 2 basis vectors are much longer, and they're also more skewed. There's less of a right angle between them. So you can kind of see that it's a little bit harder to figure out how to write a random element of this lattice in terms of this basis vectors. Now think of basis vectors that are much, much longer, like their endpoints are halfway around the world, and they're very skewed. So in general, if you're given a lattice in n dimensions with a random basis set of basis vectors, it could be very difficult to figure out how to find short vectors in this lattice and how to express random lattice vectors in terms of this basis. So that's really the hard problem here. Unfortunately, I've showed it to you in 2 dimensions, which is kind of silly because it's actually not a hard problem in 2 dimensions at all. We have what's called the Gram-Schmidt orthogonalization process that you can use. So just very briefly, let me explain that you can take one of these basis vectors and you can project it onto the other, and then you can subtract the projected vector, and you'll get a shorter vector for this one. And then you can project that onto the other one and subtract, and then get a shorter vector for this one. And you can keep going like that. That's called Gram-Schmidt orthogonalization, until you get the shortest vectors for the 2-dimensional lattice. So that's a very easy process. But the problem is that it doesn't work in n dimensions. So the very famous LLL algorithm, Lenstra-Lovász, was from the, the late 1980s, I think, showed how to use this idea in n dimensions. So you take pairwise, you take 2 vectors at a time, and you do this until you can get a much shorter set of basis vectors. So I'm not going into details of exactly what order you do everything in. And this algorithm runs in polynomial time. It's a classical algorithm and runs in polynomial time, but it does not guarantee that you get the shortest vector. In fact, the vector that you end up with following this process is only guaranteed to be an exponentially bad approximation of the shortest vector. So its length could be up to like 2 to the n. It's actually like 2 to the n over 2 times the length of the shortest vector. So it's a good algorithm, and it's used throughout mathematics and computer science for many interesting things. But it does not kind of conclusively break lattice-based cryptography, because it doesn't actually find the shortest vector. It finds an exponentially bad approximation to the shortest vector. And so what is used today is a generalization of LLL called BKZ, the BKZ algorithm. And so you, instead of taking vectors kind of 2 by 2, you take a bigger block size K, where K is anywhere between 2 and the dimension of the lattice. And K is the number of vectors that you kind of put into the mix, where you kind of project vectors down onto each other to create smaller lattice vectors. So the high level idea for how we use, let me see how much time I have left. So I have about 15 minutes, is that right? And maybe I'll even try to end a little early if I can. So I've described so far what is lattice-based cryptography and what is the hard problem. The hard problem is given a lattice to find short vectors, find a short basis, or to find the shortest vector. So how are we going to use this for cryptography, for encryption? So the idea is that any message that you would want to send or encrypt, you have to convert it into this space, this basically this vector space, into a lattice vector. And then what we're going to do is use a very common strategy in cryptography for encryption. It's called blinding. So we're basically going to add a secret inner product vector to your message, and that way it's like the idea of a one-time pad from cryptography, which is that it should be randomized. It should be different every time. So every time you encrypt the same thing, it should look different. You get a different randomness each time. And so you don't know what your message is, because there's just some secret random number that's been added to it. And so what you don't know what the message was and what the secret random inner product vector was. So the way that it works is that you provide the randomness along with the ciphertext includes the randomness, but not the secret. The secret vector you keep secret. So the only problem with this strategy is that if an eavesdropper were to intercept a bunch of these encryptions, what they would be able to basically do linear algebra to figure out what your secret was. But instead, what we do is we actually add a little bit of error to each message. So you have a message and you blinded it by adding a secret inner product. And now we're going to add some small error. And this error vector is actually selected from a certain distribution, which is typically taken to be a Gaussian distribution, meaning it's a lot of small values right around the origin and a lot less likely to have taken some larger values for the error. So think of the error as being some small error that's been added. And so when you get this encryption, if you have the secret vector and you get the randomness, you can create the secret inner product yourself and you can subtract that. And then all you have is the message with a little bit of this very small error, and the error can literally be rounded out. And so that's how you can decrypt if you have the secret. But if you don't have the secret, the problem is you're stuck with some basically noisy vector. It's not in your lattice. It's slightly a little bit far away from your lattice. Let me see, I have a picture here. So think of the dots as being the lattice vectors, and an encryption would be one of these circles here that's not in the lattice, but it's close by. And what you would have to do is you would have to be able to decrypt or decode really to the nearest lattice vector in order to be able to try to break the system. So the hardness of this crypto system really depends on what we call bounded distance decoding and kind of the hardness of the shortest vector problem. So just to connect it to another part of mathematics, in fact, what made this very exciting, both for NTRU and for ring learning with errors for homomorphic encryption, is that it involves another branch of mathematics, number theory, through the use of polynomial rings. So instead of lattice vectors in our implementations, you know, a lattice vector just has n coordinates. It's just n entries. And in fact, what we're going to do is we're going to think of each of those n coordinates as the coefficient of a polynomial of degree n. And so these lattice vectors, instead of being vectors, they're actually polynomials, and we can add and multiply them. So that's where you get the homomorphic property from, is we've converted everything into polynomials, and we're basically just adding and multiplying massive size polynomials. And so that's where a lot of the optimization comes in, is to being able to do these kinds of operations, adding and multiplying very high degree polynomials with large coefficients very efficiently. So I'm not going to talk too much about the error growth problem because in the interest of time. I think I'd like to just skip forward to some of the applications of homomorphic encryption. I've talked a little bit about the breakthroughs in machine learning. I mentioned a little bit the ring learning with errors problem. And if you have questions, I can explain a little bit more about that later. But as you can see, if you're a number theorist, you'll probably be happy to see this nice number ring here, which is the ring of integers in a cyclotomic number field. And so there's nice problems I led a group with Kate Stang at the Win3 conference, and we wrote a paper called Ring Learning with Errors for the Number Theorists. So if you want to read something about ring LWE from a number theory perspective, I suggest looking at that paper. And there's some nice open problems there that people in number theory have been working on since then. And I've mentioned the security of the lattice-based systems. And in fact, what we've actually done is we've created a whole community called homomorphicencryption.org to basically not just study, but use all of the results of the theoretical lattice crypto community to quantify the best known attacks on lattice-based systems and to recommend parameters for use, for practical use in homomorphic encryption. So if you just look at the top line of this table here, so let's say you take a lattice, which is dimension n. So it's going to be a power of 2 for reasons that I didn't explain. But in this case, it's 2 to the 10. So 1024 dimensional lattice. Then what we recommend for homomorphic encryption is using a finite field, which is FQ, where Q has like 31 bits. So it's a large prime, which is roughly of size 2 to the power 31. It takes roughly 31 bits to represent each element, mod Q. And then we quantify the best known attacks using like shortest vector, like approximate shortest vector algorithms, or decoding, or dual lattice attacks. And so these are actually, this is not the most recent version of the standard, but because some of these columns have been kind of combined. So what you can see is that this 130, this is estimating that the time it would take you to attack these parameters would be 2 to the power 130. And the US government standard for cryptography is 128. That's the minimum security level, is 128. And that means best known attacks run in time at least 2 to the 128. So that's why we picked these parameters. So this community, homomorphicencryption.org, I helped to launch in 2017 when I was at Microsoft Research, and we created a whole community of people working on applications of homomorphic encryption. And so we've worked in a lot of, biology applications. There's a whole community that does secure genome analysis using homomorphic encryption. And that's the IDASH competition that happens every year. I encourage you to look up, it's humangenomeprivacy.org if you want to see the IDASH competitions. So I worked on a lot of applications. And then in 2015, my team at Microsoft, we started to build Microsoft Seal, which is the simple encrypted arithmetic library, and eventually released it open source in 2018. So if you want to use our implementation of homomorphic encryption, you can go to sealcrypto.org and find the code there, which you can use to try to fool around with. So we really had great hopes for this homomorphic encryption technology. This is the standardization community that's worked over the years. These are many other publicly available homomorphic encryption libraries that have been developed by companies and groups of researchers over the years. So you can go to the homomorphicencryption.org website and you can find links to all of these open source libraries. You can also see here kind of how the performance of homomorphic encryption has come down over time to make it much more practical. So that's the thing that you'll often, people, if you've heard of homomorphic encryption already, you probably think of it as a very impractical technology. And a community of researchers, including mathematicians and computer scientists, have really worked hard to bring down the performance overhead over time, and are now even working on hardware acceleration for homomorphic encryption. So there's a US Department of Defense DARPA projects that are funding research into hardware acceleration for homomorphic encryption. So I usually like to end my talk by showing talking about some applications of homomorphic encryption that might seem a little bit more real. I used to show demos. There's many recordings of me giving talks of demos that we built with my team at Microsoft Research showing homomorphic encryption. So like I said, in 2014, one of my favorite demos was to show heart attack risk prediction. So I actually input my own personal data and uploaded it in front of a live newsroom at the AAAS meeting. And my risk of having a heart attack was predicted by the model in the cloud using my encrypted data sent back to me on the laptop. And I was able to decrypt the answer and show it to everyone. And that whole round trip was less than 1 second. So, and that was like 8 years ago. So I was trying to show how practical this technology was even then. And like I said, since then, we've used it to show deep learning predictions. So CryptoNets showed recognition of handwritten digits. The MNIST data set, which is a classic data set used to benchmark machine learning algorithms. We showed genomics and health applications, so showing the flowering time, like predicting from the genome of a flower using like 200,000 SNPs, like genome coding locations on the genome of the flower to predict the flowering time of a flower. We showed pneumonia, your risk of dying from pneumonia, given like 48 characteristics when you show up in the hospital with pneumonia. And so the list goes on and on. More recently, we actually, in 2019, we showed As Your Run was a private fitness app. So if any of you use like a fitness tracker, instead of uploading all of your location and your private data about your fitness workouts to the cloud in unencrypted form, it handles only encrypted data uploaded from the app and still shows the same kind of functionality for your fitness app. So this was a proof of concept to show that there are cloud services which currently use your private data, which could be just as well built on encrypted data, and so that you wouldn't actually share your private data with the cloud. And another example of that was a secure weather prediction. So if you have a phone that has a weather app on there, then you can see the weather, but it uploads your location through your zip code. Whereas you could also provide a private version of the secure weather app by only uploading encrypted versions of your zip code, and you would still get a prediction of the weather, but the cloud service would not learn your location in order for you to get that information. So that concludes kind of the applications that I wanted to highlight and outline. I wanted to end a few minutes early in case there's questions or discussion. I have more applications that I could tell you about, but why don't I stop now and hopefully take some questions. So thank you so much.
Thank you, Kristen. That was very, very interesting. And yeah, so Kristen mentioned at the beginning that she is also willing to answer questions if you have any questions about also not only her research, but her kind of career path, right? Because she spent a lot of time in Microsoft and now she's at Meta. So if there are questions about that, I think we could spend some time also. At the moment, I don't have any. So,
well, I could just say a few words about, I work, so I lead West Coast Labs for Meta, for what used to be called Facebook, formerly known as the company formerly known as Facebook. And in our labs, so Meta AI research is focused on just AI research. So when I was at Microsoft Research, there were many, many groups across all areas of computer science, including cryptography, which I led, cryptography and privacy. I also started an urban innovation team there. But there was a lot of, data science and algorithms and all kinds of human-computer interaction research groups. But at Meta AI, we're just focused on AI. So the teams in our labs that I lead are world-class researchers working on areas such as computer vision, which uses AI, natural language processing, uses AI, robotics, a lot of research into robotics and kind of an embodied version of robotics that is important for the vision of the metaverse. And then there's also more mathematical groups that are the core machine learning. So core ML and reinforcement learning are more focused on the mathematics of machine learning. And so I have started a new group, which is a privacy and socially responsible AI group. So private AI related to the topic of this talk, but other privacy enhancing technologies as well. So I don't know if anyone has any questions about mathematics in industry.
I think I do have a question about the mathematics, but you mentioned, now that we have a couple minutes left, if you could like walk us a little bit through the real learning with errors bit.
Oh, sure, absolutely. Thanks for asking. So let me see if I can go back to the slide that I had there. So what I mentioned was that instead of just thinking of lattices as a vector space, we're going to think of them as a polynomial ring. So when I was showing pictures, we were thinking of the real numbers, but in fact, what we really need to do is everything, to be able to put it onto a computer, needs to be discretized. So we actually have to kind of cut things off and choose a size So Q, the number Q is usually, for number theorists, it's usually prime, because then we can think of as a finite field, FQ. For the lattice crypto people, Q might not even necessarily be a prime, but for our purposes, we think of Q as being prime. And then what we're going to do is we're going to think of these coefficients not as being real numbers, but as being elements mod Q. So now we have vector spaces over FQ. And there's a way that you can map any number ring. So we're going to take the number field, which is just cyclotomic number field with nth roots of unity adjoined. And this RQ is just the ring of integers in that cyclotomic number field. And you can think of the embedding of this number field into the complex numbers, like into like C to the N, where C is the complex numbers, using the Minkowski embedding. So every element, every algebraic number in this ring is embedded into the complex numbers via taking its image under the n different, basically Galois automorphisms, all possible embeddings into the complex numbers. So that's the relationship between the lattice that I was showing you the picture of in Euclidean space and the lattice that we actually use in practice, which is this mod Q number ring, essentially. And so one of the interesting security issues, and that's what we wrote about in our Win3 paper, is that the distribution that you see of lattices in real space, which is like the Gaussian for the error you would take would be cylindrical, that can be distorted by this Minkowski embedding. But for cyclotomic rings, which are where n is a power of 2, this embedding is not distorted, and it's like the perfect match. So that's why we use 2-power cyclotomic rings. But if you use a different number ring, what'll happen is that embedding can kind of, instead of being like a circular spherical error distribution, it can be like elongated or distorted, and so that you'll end up with a very bizarre kind of error distribution using this back and forth recipe. And so that's why we stick with, for security reasons, we stick with 2-power cyclotomic rings. So I think really interesting problems. I mean, we showed many different rings that you could use that would be insecure. So we found in our Win3 project, we published a paper in Crypto 2015, I think, which is a very competitive publication venue for crypto. We published our paper showing rings where this ring learning with errors problem was insecure. And then we continued working on this with my intern, Kate Stang, and I worked with Hao Chen, and we published a paper in SciAga, which is a SciAm journal, on algebraic geometry, showing more rings that are actually insecure. So for the RLWE problem. So there's still interesting number theory work to be done in this area. As I mentioned, the ring was called RLWE for the number theorist paper that we published in the Win3 proceedings, I think is a nice place to start for anyone who might want to look, who's a number theorist, who might want to look into this area. Does that help, or would you like me to answer any other specific questions about ring learning with errors?
No, I think that answers my question. Yeah.
Great.
Thank you. Yeah. Well, I think we don't have any more questions, and we're also running a little bit short time. So thank you again to Professor Christine Lauder for today's plenary lecture for the Simposio Internacional de Métodos Matemáticos Aplicados a las Ciencias, organized by the SIMPA and the University of Costa Rica. And thank you everyone today for joining us. Muchas gracias a todos por unirse, y recordarles que todavía tenemos en la plataforma global UCR todavía se pueden dejar preguntas. Hay una pregunta de Ronald.
Yes, Catalina, thank you. Thank you, Kristen, actually, for your interesting talk. It was really, really nice. We really appreciate from the organizing committee that you are here to share your knowledge. And thank you so much, Catalina, for the chair today. From the organizing committee, we really appreciate your help. Thanks once again.
Great, thank you. Thanks, everyone. Mucho gusto.
Mucho gusto, gracias.